Since your test is focused on mechanisms, I decided to make the example just complete mechanisms, so we'll go ahead and get started right away. So with this first one, we have this doubly stabilized enolate, since we're in basic conditions. So since we have the ethoxide, that would come in and take off a hydrogen to form the enolate. Well, what that's going to create is a nucleophile, a chance for that we can actually attack something else. So if I have the double bond right here, draw this out real quick, just draw that thing. Well, the next thing we add in the solution is this alkyl halide, this bromine. So we can have these electrons come in the oxygen, have the electrons in the double bond come in and attack and push off the bromine. Well, what that does is it actually eventually adds an alkyl group to the negative charges there. We have a double bond in oxygen again. This one over here is fine. The oxygen and the ethyl group, and we added an ethyl group. Well, as you can see, if we look up in the reaction, the same thing happens here by adding another base, since we have another hydrogen over here. Well, the thing is, we actually have a different alkyl halide. So what we'll do is we'll just end up adding this R group. So for the sake of time, I'll go ahead and draw the result of that, of steps 3 and 4, and that would end up being this. So we have these two alkyl groups, or R groups, that we added, and we still have our ester, so we have the 1, 2, and then for the other R group, I have these 4 carbons. It kind of looks like a sec-butyl, or isobutyl, excuse me. So if I draw that, I would have 1, 2, so kind of messy, but we'll work with it. So this is what we have now, and this is what it would represent what we have for our question mark right over here. Well, the other thing we have to do is, I'll erase that arrow for room, is that we have to think, what is going to happen with the hydrolysis and heat? Well, once again, to save time, for the sake of time, we can look at this and think, okay, I have this ester right here, and if it's hydrolyzed by acid, that's going to turn this into a carboxylic acid. So if I go back and I just go ahead and erase this part, which won't let me do, so I'll go ahead and redraw the molecule. I have this part, this, carboxylic acid, and then our 2 R groups. Well, from here we need to consider what's going to happen when we actually add heat in the acid. Specifically what's going to happen to this carboxylic acid part. Because we see in our product that we've lost that. We've lost the carboxylic acid during decarboxylation. So typically what you want to do is, I'm going to go ahead and draw this stuff up here. You want to write your product in a certain orientation so you can move the arrows effectively. So here we have this, and what I'm going to do is I'm going to put my hydroxy group on the carboxylic acid up here, and my double bond oxygen here. So it's just as if we spun what we had. Well, now we can look at the arrows. And what's going to happen is you're going to have these electrons come and grab this hydrogen, which will free electrons in the oxygen to form a double bond right here. Well, that means the electrons between this carbon and this carbon, they have to leave. So that means they'll end up being pushed over here to form a double bond between the carbon and the other carbon, and that would push electrons up here. So you see the circular movement of electrons. Well, the result of that, if I draw that down here, is for one, we got a decarboxylation to the CO2 left, and that CO2 is formed right here. So if I draw this, we kind of reform the enolate again. We have double bond here, and then from there, the carboxylic acid CO2 is formed, and then from that point we also have our 2 R groups. Well, from there what we'd expect is to get the final tautomerization. These electrons would come down, and these electrons would come and grab a hydrogen since we're in acidic conditions, and that would get us to here. So I know this slide and the one that I just did is pretty messy. There's a lot of steps, but I will include a drawn-out answer to this so you can kind of work through it. And that way you can follow my voice on that and follow what I've written out, since we don't have as much space to work with here. Sorry about all the background noise in the last one. We'll just go ahead and continue with this slide right here. So the first part, since we have base, I'm going to write that way too big and messy. Well, we know we're going to abstract a proton here, which I need to draw. Those electrons will go up and push electrons up onto the oxygen. So the result of that is, if I draw that, our enolate. Well, we have to ask ourselves, if we create an enolate which acts as a nucleophile, what can it attack? You still have this aldehyde in solution. So these electrons on our nucleophilic molecule can push electrons down. Those will push electrons up to here to attack this. Well then, if I go ahead and draw the result of this, I have the aldehyde that's reformed, that did the attack. Then I have oxygen over here, H, and that's, I'm saying that would be protonated at this point, just because over here we'd be in basic conditions and we'd protonate afterwards. Well, if we have heat, that's going to allow us to eventually deprotonate. Do the dehydration. So we have a hydrogen right here. I still have the hydroxide. You come in, pull electrons up, recreate the enolate. Well, the result of that is I have my enolate part, have my OH, we haven't touched. Well, what happens here is we have these electrons come down, these electrons move all the way over here and kick off the OH. And that gets us to this point, which is, so this is exactly what we've seen before with an aldol condensation. The next question is, how do these interact, these two nucleophiles that we have here, the lithium cuprate at the top and this Grignard reagent, how do they react at these positions over here? The first thing we can notice, we can ask ourselves, what type of nucleophile is a lithium cuprate? Well, it's a soft nucleophile. That means we're going to be reacting at this position right here on our molecule. When you're doing with the lithium cuprate, you just pay attention to the R group they have. In this case, it's an ethyl group. So the result of that, if I draw this down here, will be this. And typically with the lithium cuprates, you don't have to show a lot of the mechanism. Well, what's added next? We have our Grignard reagent. And that we expect to react with this carbonyl group. And we've seen that before. So if I were to draw this, I would have, just do the pH for the phenyl group, Grignard. These electrons would come here, push electrons up here. And that last step with the hydronium, that would just be a protonation. So our final result we get in terms of the mechanism is this right here. So that one wasn't too bad. For this one, if we're starting in acidic conditions, we have to ask ourselves, well, what's available to be protonated? In this case, the one thing that comes to mind is protonating this carbonyl group right here. And at first you might ask yourselves, well, why would you protonate that first before mixing with the nitrogen? It'll make more sense when we look at this next part of the mechanism, because this part that we just did has to happen in order for the reaction to continue. If we've protonated this carbonyl group, well, oxygen's really thirsty for electrons, and we want to eventually attack this carbon right here. Well, what's in solution to attack? We have the electrons on the nitrogen. They can come over, push electrons up. Here, it's really important to make sure that you're counting your carbons, since we are forming a ring. Here I have 1, 2, 3, 4, 5, 6 atoms that are going to be in the ring. So here I'll draw the place where I created my OH. So you have that 1 carbon, 2, 3, 4, 5, 6, and then it has 2 H's. So then put a positive charge on the nitrogen. Well, eventually we know we'll deprotonate that, so we can draw that. Just imagine that had happened. And then we think, okay, well, things still have to continue. So actually I'm going to have to draw that out. You have that hydrogen, and this oxygen. Well, we want to get rid of that oxygen eventually if this is going to continue. And we're in acidic conditions, so we can protonate. So if I protonated that, put a positive charge on the oxygen, well, how are we going to kick these off? How are we going to kick that the water off? What electrons do we have to do that? On our nitrogen, we have a lone pair, so if those come down to form a double bond on the nitrogen, we can kick electrons up onto the water to get it to act as a leading group. And the result of this is this. Excuse my bad handwriting. But we have this right here. We have a positive charge on the nitrogen. And of course next we just end up doing the proton transfer to get a neutral molecule. From here, if I go ahead and draw the result of that proton transfer, just so we can work with a neutral molecule, I have this. The next step we have is this reducing agent. So we're going to be adding a hydrogen here, and we're going to think, where would we add? Where would we expect to add a hydrogen? Well, that's going to act essentially, if we draw this out, act as a hydride donor. That's typically how we do these reducing agents. So we draw all this negatively charged. This is going to act as a hydride donor, push electrons up onto there. And what we'll eventually get is we have the nitrogen single bond negative charge because we moved electrons up onto it, and we'd eventually have to protonate that. And it's going to get us our final product. So here the overall transformation, we went through all of the mechanisms, is we ended up taking this primary amine and making a secondary amine. But in this case, it was actually an intramolecular reaction because the amine we had over here reacted on the same molecule with the ketone we had to the left through these acidic conditions and eventually a reduction. For this one, since we know that we have a base at the beginning, we can assume that we're going to be abstracting alpha hydrogen. But here we need to consider which alpha hydrogen we're going to abstract. So look, we have a few choices, the ones that I'm circling right now. Well, we need to consider what happens next. What's going to allow us to form a type of ring, because it's intramolecular. Well, I just counted 6 carbons, that'd be good. If I do that other one, that'd only be 4, and if I start from there, that'd be 4 as well. So I'm going to take the alpha hydrogen at the end, because that's going to allow me to form a 6-membered ring once I do the attack. So I'm abstracting the hydrogen, electrons go up onto the oxygen, and I'll draw the result of that. So we formed the enolate. You have to excuse the noise in the background. I haven't had the best chance to make the best video. But here we see that the enolate has been formed. Well, what happens next is electrons come back down, and then we attack our carbonyl position. And what we get, that forms a ring, and we know we formed a 6-membered ring, so that's what I've started drawing right to begin with. Now from here we have the carbonyl group, and then we'll have the tetrahedral intermediate. So what I'm doing now is I'm counting the carbons to make sure I place my tetrahedral intermediate at the correct place. So 6 carbons, and 6 carbons, the end, right there is where I'm going to put my tetrahedral intermediate. We have a O negative group, which is where we got when we push the negative electrons up onto the oxygen. And we have our ethyl group. Electrons will come back down, as we're used to kick off the ethoxy group. When we get there, we will have formed another carbonyl group. So we'll go ahead and draw our 6-membered ring again. We have one carbonyl group and the other where we kicked off the ethoxy group. Now the thing here is, are we done or not? That's kind of the question, and this is a bit tricky because the reagents I have up here would make you think that we can do a decarboxylation. But do we have a carboxy group over here? We don't. So that's why we have to consider that this is actually working, we've gotten to the end. I'll apologize in advance because this one's going to get a little credit on the screen. So here in the first step, we know our nucleophile is the azide. It's going to have those 2 negative charges, positive charge and net -1 charge. Those electrons in one of the nitrogens will go up and attack our starting material to kick off the bromine. It's just an alkyl halide. And that's going to add the azide to our R group, which I went ahead and drew out all the way. So as I'm finishing drawing up this azide part, we want to ask ourselves, this next step with the lithium aluminum hydride, where does that come into play? Well, we know the aluminum hydride is a hydride donor. And we're in the process of creating an amine, so we know that the hydride is going to donate to that nitrogen at the end, and it has to push electrons up onto the nitrogen with a positive charge. Well, that makes sense. If a nitrogen has a positive charge, or if any atom has a positive charge, then it wants electrons, and we want to free electrons in order for that to happen. So I'm drawing out the rest of it. We would have moved that double bond to put electrons onto the nitrogen. That would make it neutral, and we still have the negative nitrogen at the end. Well, what's going to happen with those lone pairs? They're going to come down and form a triple bond, and then that's going to, in a way, kick off the whole group that will have our amine. Now keep in mind, when we form a triple bond between the two nitrogens, that creates nitrogen gas. So that will actually boil off in the reaction. And here, that leaves us with our other part, the R group of the amine, will eventually protonate to get this primary amine. And we look up, we want to consider if we have this carbonyl group in the next step with acidic conditions, what will that look like? Well, in this case, we know for an acidic conditions, the carbonyl group will eventually have it protonated, which activates it for an attack. And, well, what's going to attack here? We'd expect our nucleophile, which is the amine, to come in and attack at that position. And like I said before, this is where it starts to get a little bit crowded in terms of the screen, so bear with me here. Once we get that attack, we'll draw what we essentially is a tetrahedral intermediate in a way. Just we'll have a positive charge on the nitrogen, because it still has two hydrogens. And we have the hydroxy group, which is creating when the electrons moved up onto the oxygen. Well, we'll do a deprotonation. I'm not going to draw out the full thing. That's going to make our nitrogen neutral. And we'll eventually protonate the hydroxy group so we can actually get it to leave. Well, how are we going to get it to leave? This is where I believe I'm actually going to have to move this to show that reaction, and I'm going to move it up. Once again, sorry about the lack of space. So I'm going to draw this out all again. And our electrons are eventually going to come from the nitrogen because there's a lone pair there. So when we're moving those the lone pair down, we can get water to act as our leaving group. And it's going to eventually create an imine. Now, I'm running out of room, so I'm going to have to get to a point where I'm going to have to erase quite a bit of this and draw this again to show the final product, which is we're just going to see the imine created since we created a double bond between the nitrogen and the carbon. So I'm going to finish up drawing that, and in this case, that's all she wrote. So in terms of this video, I tried to focus on the mechanisms, going through them. I apologize, it's not one of my best videos. It's pretty messy, but hopefully if you have any other questions, you can just email me, and email jakemorgan@ou.edu. Besides that, good luck on the test. And also sorry about all the background noise.